Dear students, today's topic is the EMWP-S9, that is electromagnetic wave propagation, section 9. The topic title is solution of plane monochromatic wave equation traveling in a conducting medium. Last time we did in the section 8 the traveling of EM wave or electromagnetic wave in a non-conducting medium. So this slide consists of 5 pages. We will go through one by one. So this is page number 1. We have the plane monochromatic electromagnetic wave, which is a position dependent ES electric field, E field, S for the space dependent or the position dependent wave equation, which is given as del square of E plus omega square epsilon mu E of S plus J omega mu E is equal to 0. This is equation number 1, where J is the obviously complex the part which is equal to under root -1. G is the conductivity, epsilon and mu are the permittivity and permeabilities respectively. Omega is the frequency, angular frequency. So G is the conductivity of the medium. So now let us consider that the wave is moving along the positive z direction and its amplitude is E naught, which we also considered last time, and is having an xy plane as E naught x and E naught y. So this one is the E naught x, the vertical one is E naught x, and the is the coming out of the plane of the paper is E naught y, and the wave is moving along the z, which is k unit vector. Equation 1 is written as, since now we consider only the propagation along the z direction, one dimension is we are considering only the function is dependent on the z. So the equation del square, the three-dimensional del operator, will take the form of the exact differential, the second order differential, which is d2 by dz square E plus omega square epsilon mu E plus G G. There are 2 G's, but let me correct those. Okay, so plus J omega G mu, it must be omega G mu E is equal to 0. This is equation number 2. Now let us consider that E field function is described as E naught, which is amplitude e raised to power j gamma z, where gamma is now the inside the conducting medium. We will be calling in attenuation constant or the propagation constant. In the previous case, for the non-conducting medium, we took the k instead of gamma. Since we are now in a different medium, so we are taking a different attenuation as well over here. So now taking the differential of this equation, which is a function we take, that is E of sz. If we take the twice differential, we get the minus gamma square E naught e square j gamma z. Putting this result of the second order differential, differentiating this E in this back into equation 2, we get this minus gamma square E naught e square j gamma z, and you can see the e square j gamma z is common in all these terms and is cancel out, and we are left with the minus gamma square plus omega square epsilon mu plus the j omega g mu, which is equal to 0. We can write gamma square, rearranging this equation above, gamma square is equal to omega square epsilon mu plus j omega g mu. This is equation number 3. Now let's take that gamma, which is a we can see here it is a complex part. The complex equation, complex function is equal to some alpha plus j beta. Now putting that in equation number 3, we said the gamma square is equal to alpha plus j beta whole square. If we open up this square, we get the alpha square minus beta square plus 2 j alpha beta, equation number 4. So now put this equation number 4 in equation 2, replacing gamma square, which is the this term, this alpha square minus beta square plus 2 j alpha beta. So we after putting that, we get the both sides now have the complex part, real and the imaginary parts. Comparing the both sides, the coefficient of the complex and the real part. So what we have got now, alpha square minus beta square is equal to the real part here, alpha square minus beta square, here the real part is omega square epsilon mu, and the imaginary part 2 alpha beta is equal to omega g mu. So these two equations we got now, 6 and 7. Now from equation 7 we can write that beta is equal to omega g mu by 2 alpha. Now putting this term, beta term, in equation number 6, so what we get, alpha square minus, this is putting the value of beta, omega g mu by 2 alpha whole square. This is the right hand side, which is omega square epsilon mu. Now after simplifying the equation, we get that here this, opening this term as well, which is the 4 alpha square, and this 4 alpha square multiplied with the alpha square is 4 alpha 4, and so on, minus 4, which is the omega square. Rearranging the things together, we get the equation number 8. This 4 alpha square goes to the other side, which is 4 alpha square omega square epsilon mu. We take it to the left hand side, which is minus 4 omega square of the alpha square, here alpha square epsilon mu, and the other term, which is the omega square g square mu square. Now equation 8 is a quadratic equation, and its solution, which is the of the form, we can write ax square plus bx plus c is equal to 0. We can take a as a now 2, the alpha, we can take as the a as a 4, and x square is alpha square. Okay, so similarly b, you can see all the terms, relevant terms, we can find a is equal to 4, b is equal to minus 4, 4 omega square epsilon mu, and c term is here minus omega square g square mu square. So putting these respective values of a, b and c in this, we can get the value of x. So it's a quadratic equation we are looking for. So x is now alpha square, which is of 4 omega square. Here we have the quadratic equation. Now we have this alpha square 4 omega square epsilon mu plus minus inside the term, which is b square minus here we can see that 4ac divided by 2a. Putting the respective values, since I have provided this, all the hard copies, you can check that in the same pages have been posted on the website. You can download it and print it and see all the calculations. So we get ultimately here at the end alpha square value, this one, then we take now the square root of both sides, we get the alpha. So alpha is equal to plus minus omega epsilon mu root plus 1 by 2 plus minus 1 by 2 1 plus g square over omega square epsilon square whole square root. Since beta is equal to omega g mu by 2 alpha, now putting the value of alpha in this equation, beta, we get beta omega g mu plus minus 2 omega epsilon mu under root 1 over 2 plus minus this whole term of the alpha. Now the plane wave traveling in the positive z direction with time dependent part is given by the E of z comma t is equal to E of z e to the power minus j omega t. Since E of sz is E naught e to the power j gamma z into e to the power minus j omega t. So again here the powers will be added. We get the E naught e to the power j. Here the gamma part we take the alpha plus beta, and here we get the over here the term, putting the here the value of gamma is alpha plus j beta and j times gamma, and rearranging the things we will get this relation E naught is for j alpha z minus omega t, which is j is common to both, and E is for minus beta z. Putting now here we have put that alpha plus j beta. So in the next page 4, which we get equation 9, represents an exponentially damped wave traveling in the positive z axis inside a conducting medium, where the e to the power minus beta z factor is called the damping part or damping factor, as beta is omega g mu by 2 alpha, containing the g, which is the conductivity part, which is in the denominator 1 over e to the power beta z, offering the resistive part, causing the damping. So that causes the damping inside the medium, to the wave, traveling wave. Now let us solve for the the magnetic field part, B field function. We have the Maxwell's third equation, curl of E is equal to minus delta B by delta T. So again, considering the B as a function of space and time, is z and t, B of sz e to the power minus j omega t, taking the differential of B with along with the negative sign, we multiply the both sides, but we get j omega B of z t, is equation number 11. Now taking the left hand side, which is the curl of E, again taking the matrix or determinant rule or the procedure to solve or resolve it, which is again I, j, k, or the del and the E vectors, unit vectors I, j, and k, delta by delta x, delta by delta y, delta by delta z, and E naught x with the exponential part, and E naught y with exponential part, and the z part is 0. So ez component, the z part inside the plane, which is in the xy plane, so propagating along the z, but the actual component of E is not there. So after simplifying this, which we get the curl of E of, which is z of z and t, j times alpha plus j beta, this whole term, minus E naught y plus j E naught x e is for this whole term. Rearranging the things, so what we get, this term again is the k cross E naught e to the power j gamma z into e to the power minus j omega t. So comparing equation now 11 and 12, we putting these values and comparing both sides, what we get, some terms are cancelled out, j is cancelled out, e to the power minus j omega t is cancelled out. So we are now left with the solution of the B, which is B of sz gamma by omega k into e to the power sz. So this is the position part, space part, Now we can put that value in back into the space and time both, but we get gamma over omega k cross E naught e to the power now j gamma z minus omega t. So minus omega t part is now here the additional minus omega t is in the exponent form is added here. So the equation 9 and 13 which we get is the solution or the solutions for the given wave equation in terms of E and B. So we reach to the end of this topic S9 EWP-S9. Thank you very much and see you next time inshallah. Thank you.